The next speaker is Madeleine Cule, and she's going to be talking about nonparametric estimation of a log-concave density.
Thank you very much. My name is Madeleine Cule, and I'm a PhD student in the Stats Lab here in Cambridge, and I'm going to talk briefly about some joint work I've been doing with Richard Samworth and Bobby, who's been very busy, and also with Michael Stewart in Sydney, who suggested this problem in the first place. Oh no, I don't have to do that. Okay, so the basic problem I'm going to be talking about today is a very simple one and quite a fundamental one. So we assume we have IID observations taking values in RD or some subset of RD from some distribution that's assumed to have a density, and we're thinking about how we should estimate the density. So there are all sorts of applications. All sorts of things this could be used for sort of exploratory data analysis, clustering, functional estimation. I'm going to be talking about a particular framework for doing this. So here's a quick outline of what I'll be talking about. First of all, a brief bit of background. Then I'm going to be talking about the particular model we've been using, thinking about log-concave densities. We're going to see how we can use maximum likelihood in this approach. I'll talk briefly about how you actually compute the maximum likelihood estimator, especially for sort of d greater than 1. Look at a couple of synthetic examples, sort of sample application, and then finish with kind of what we're thinking about at the moment. So that's what I'm going to talk about for the next few minutes. Okay, so we're trying to estimate this density. And the sort of classical way to do this is to use some kind of parametric approach and to assume that the density belongs to some finite dimensional family indexed by some kind of parameter, with k being quite small there. And then we can just estimate the parameter. Obviously, there are many ways to do this. One particular method that has sort of nice theoretical properties is maximum likelihood. But really the problem with parametric models, I think, is how do we know which class to pick? I mean, sometimes there's no obvious way to assume it has a particular form. So this is something Fisher called entirely a matter for the practical statistician, and then sort of ignored that one. But anyway, we're going to see how we can maybe relax that. So at the other end of the scale, you have these non-parametric methods. So if we don't make any sort of assumptions on what the density looks like, and we just assume it's a density, then we can't use maximum likelihood, basically because the likelihood in that case is unbounded, because you can make the density arbitrarily spiky. So we need to do some kind of smoothing to actually get a density out of this. So one example I've written up here is to use a kernel density estimate, where we put a point mass at each observation and sort of spread it out a bit till we get a whole density. But the problem with this kind of approach is we need to decide how much smoothing we're going to do, and if you get it wrong, that will obviously affect the performance of the estimator. And choosing the amount of smoothing is much more difficult if we have multivariate data, because you need to smooth in each direction, and there aren't really good rules for doing that. So there are lots of other non-parametric methods, but they all basically have this problem that you need to choose how much to smooth. So we're going to be thinking about a non-parametric or sort of infinite dimensional model where we don't have to choose how much smoothing we do, but we can still use maximum likelihood. So the idea is that we pick an infinite dimensional class of densities sort of characterized by some qualitative shape restriction. And if the shape restriction is kind of suitable, basically if it stops the density from getting too spiky, then we can still do maximum likelihood in this setting. So this idea goes back to the 50s, Grenander, who thought about monotone decreasing densities in the context of actuarial data, life expectancy data, and he kind of characterized the maximum likelihood estimator, and then since then there's been a lot of work on the theoretical performance, and that's pretty well understood now. And there's also been work on other classes of densities. But what I've been thinking about in particular is log-concave densities. So this sounds like a kind of an artificial property. So we say that f is log-concave if its logarithm is concave, which sounds kind of quite abstract. But this includes a lot of parametric classes, for example, normal, gamma, variable I've got there. So for example, the normal e to the minus x squared, the logarithm is going to be a parabola, so that's a concave function. So if we think about what these densities look like, well, they're going to be unimodal, which is actually not so well defined in higher dimensions. But anyway, have a single mode, and they have exponentially light tails. So I guess you can think of the borderline case as the exponential distribution, which is linear on the log scale. So unimodality is not actually a strong enough restriction to have a maximum likelihood estimator in this context. So you can see this as a kind of substitute, just strengthening the unimodality enough to be able to do the estimation in this way. So we also have these nice sort of closure properties, so closure under summation of independent log-concave random variables. So saying the random variable is log-concave means it has a log-concave Lebesgue density. In the multivariate context, the marginal and conditional densities are all also log-concave. And as a kind of converse, this isn't the sort of strongest converse, but if we have independent components and log-concave marginals, then we'll have the whole density will be log-concave. So it's kind of I think it's kind of a nice property to have. And the nice thing about this, I guess, from the point of view of this talk, is that if we restrict to this class of densities, we have IID observations, then there's a unique maximum likelihood estimator. So we might hope that this would be a reasonable way to estimate our density. So I'm going to talk a little bit about how you show this, because this will give us some insight into what the MLE is actually going to look like. And we'll really need that for helping us to compute the maximum likelihood estimator. So, okay, so I'm going to give a quick outline of how you prove this without too many details, because it's a bit fiddly. But we'll see how we go. Okay, so this is the problem we've got to solve to do this likelihood maximization. So these are our observations. The first term is basically minus the log likelihood. So I've written this as a minimization problem. So I've written this with WI here so to allow these, it's a bit more general, so these weights can be arbitrary, but in the sort of real maximum likelihood setting, these would all be 1 over n. So this is 1 over n sum of log fi. So this is the log likelihood here. And the second term here is a Lagrangian term, which enables us to relax the assumption that we're minimizing over density. So we're just minimizing this function over all log-concave functions. And this term this penalization will make sure that we get a density out at the end. So this kind of makes it easier. So yeah, think of this as 1 over n, the minus the log likelihood, and then a Lagrangian term. And it's not too... Oh, no, reverse. What's happened? Okay. Right. Okay, here we go. Any solution to this problem it'll have a couple of properties that will help us to compute it. So it's going to be supported on the convex hull of the data. So it's going to have a discontinuity at the edge of the convex hull, which is perhaps not quite what we want, but anyway, that's a characteristic of it. And we're actually going to get a real density because of this Lagrangian term. And the kind of key point here is that the density is going to have a particular form. So it's going to look like one of these functions. So they're indexed by a vector y, taking values in Rn. So we've got one y for each observation. And it's going to be the smallest concave function that sits on top of these yi. So I kind of think of this as you stick a tent pole of height y at each observation, and then you kind of stretch a piece of rubber over the top, and then that'll give you the form of that function. So here's a kind of diagram of what it looks like. We've got our data points here, and so for each data point we've got a sort of tent pole height here, and then we've stretched a piece of rubber over the top. So some of them, for example, this one here doesn't touch the top of the tent, but the rest of them all do in this example. So the key thing is that we've reduced our optimization problem to a finite dimensional one. So now we only need to pick the tent pole heights, which is a lot easier than trying to pick a function in this huge, great, infinite dimensional space of functions. Okay, so here we've sort of rewritten the problem we're trying to solve. We've got to minimize this function tau. So we've got minus the log likelihood here, and then the Lagrangian term here. So it's just the same as before, but we're minimizing over a finite dimensional space. But if we wanted to do this directly, it turns out not to be very practical, because evaluating this, so I mean, you might think, okay, in the worst case, you can just evaluate this function over a whole grid and then pick out the smallest. But that's not really practical, because each time you compute this is very expensive, because if you're just given the heights yi, the first thing you need to do is figure out what the function actually is, and the way to do that turns out to be to actually compute the convex hull of all these points, and that's kind of expensive. Well, it's not that bad, but if you need to do it loads and loads of times, it's too expensive. So then once you've done that, you can calculate the value of the function at each observation, and you can calculate this integral, because you can divide this piece on the bottom up into pieces where you've got kind of e to a linear function on each piece, and you can calculate the integral at the end. So that's fine, but the difficult part is computing the convex hull to find out what the function actually looks like. So we need a bit of kind of trickery to consider instead a related function. So instead of the value of the function at the observation here, we actually have the sort of original tent pole. Oh no, I've done this again. Okay, so because the two functions are related in this way, and this term here by our definition of h bar y is going to be non-negative, if we can find a minimizer of this function, sigma, then we'll also have found a minimizer of our original function. And this actually has a unique minimum, so you need to check that it goes off to infinity in all directions, but this gives us a unique minimum, because this is a convex function, which is basically because the exponential function is convex anyway. But this isn't a smooth function, so it's not possible to just use Newton's method or something like that, as we might like. So we're still left with the problem of minimizing this. But fortunately, so because it's not smooth, it doesn't have a gradient vector everywhere. But we can make use of a generalization of the concept of a gradient. So we can think about subgradients, which are at points where it's differentiable, you'll end up with the gradient, and at points where the function isn't smooth, you can pick any vector that sort of lies underneath the function, basically. And there's a kind of nice theory due to Shaw in the 80s that says that we can use a subgradient method, just like a gradient method, to minimize this function. So if we generate our points by, at each iteration, taking a step in the direction of minus a subgradient instead of minus a gradient. Then, provided we choose our step sizes to go to 0 but not go to 0 too fast, we will actually converge. So we did try this, but this turns out to be very slow, and you can do a bit of tweaking of the step sizes to speed things up, but you can't improve that much by that. But fortunately, Shaw noticed this and also proposed a solution to this problem, which basically modified, a bit like Newton's algorithm modifies the direction in which you take your step by using a local approximation. You can't use a local approximation here, but you can modify the direction in which you step to point you towards the minimum faster. And this turned out, at least for our problem, to be a really big improvement, to take it from sort of impossible to possible. So we made use of an implementation which was done by Kaplan and Konzovich as SolveOpt, and we adapted their kind of implementation for this particular problem to minimize our particular function. I guess at this point I'll just mention the one-dimensional case, which is a little bit different because in the one-dimensional case you can characterize the concavity quite neatly in that the derivative just has to be non-increasing. So that turns out, and you can't do that in more than one dimension because you just have to sort of say, well, you go down as you go out, and there's no real nice characterization of that. So this uses a slightly different algorithm in one dimension, but our version works for multivariate data as well. Okay, so now just got a couple of examples. Just a picture of this is synthetic data with 500 observations from a bivariate normal. This is the true density, this is a contour plot, and this is a contour plot of the estimate you have here. So you can see, well, you can see that we've captured the correlation there as you'd hoped, and you can kind of see we get the right shape at least. But the next picture shows a bit more what the estimator looks like. So these are independent normal observations. And this is a picture of the estimate here, so you can see that it's supported. You can see the discontinuity at the boundary of the convex hull here. And you can see it has these kind of flat pieces. And in the next slide, you can see, this is on the log scale, and here you can really see the structure of it, that it's got these sort of piecewise affine sections, and that the changes of gradient occur at these observations here, but not at all the observations. So that's the illustration of the kind of structure that you have. Okay, so the last thing I'd like to talk about is an example application of this kind of estimator. So one extension is, instead of just considering one log-concave density, we've got a mixture of log-concave components. So each of these components here is modeled as a log-concave density, and we've got a finite mixture, okay, with a fixed number of components. And I'm just going to show a quick example of using this kind of model for clustering. So yeah, that's it really. So I guess the idea is, because this is a likelihood maximization method, you can use the EM algorithm that Bobby mentioned earlier to fit a finite mixture, because, well, you know, in the maximization step you can just maximize the likelihood as we discussed before. Okay, so this was a kind of so this was an example where we used the EM algorithm to fit a mixture of two components and then attempt to use this for clustering. So we've got this labeled data from a breast cancer data set. So on the x-axis here we've got the radius of the cell nucleus, and the y-axis the standard deviation of grayscale values. And we've got two classes, the benign and the malignant cells. So the idea is that what we've done is kind of covered up the labels, fitted a cluster, and fitted a mixture, and then examined the misclassification. So just for comparison, we have a mixture of multivariate normals, which you'd expect not to do so well because this is obviously quite skewed. And we've got two log-concave components. So both of those you can use the EM algorithm. Okay, so this is the sort of result of fitting two Gaussian components. And you can see that because of the skewness, in order to kind of, well, the maximum likelihood estimate has sort of one big flat component and one here. And we had 142 misclassifications. So this was also using the EM algorithm. And then we could use this estimate as a starting point to calculate the log-concave components. And you can see that, well, you can't see so well in this picture, but these, because these components can capture the skewness, this one has kind of spread out more this way, and the second component has spread out more this way, which has reduced the number of misclassifications from 142 to 121. So here we've just shown the incorrect classifications in this example. So this is the Gaussian components, so you can see a bit more clearly that this is the one that's very spread out, and this is the smaller one. And with the log-concave component, you can see that it's captured the skewness. So I guess this isn't really what you would do with this data set, so it seems like an artificial thing to do. But I just wanted to have a little example of how it could be used. Okay, so what we've seen so far is we've seen that we can find a unique maximum likelihood estimator in a shape-constrained model. And we've seen how an iterative algorithm is needed and can be found to find the MLE. And we've looked kind of briefly at an extension to fitting finite mixture models. And I guess at the moment, the current things I'm thinking about is how to improve the computational algorithms because it's still quite slow. And the theoretical properties of the estimator, which, as I said, are understood in some other sort of these infinite dimensional models, but not really in this case. Well, at least not in the multivariate case. And also to look at further applications of this kind of density estimate. So in particular, we've been thinking about using it for functional estimation and for classification as well. Finally, there's just a few references. So this is Shor's algorithm for the optimization. Kasparov-Rebecca one-dimensional case. Again, the implementation of Shor's algorithm. Grananda, who introduced this kind of idea, and then the R package, which does all this kind of stuff, and the contents of the talk, really. Okay, thank you very much for your attention.
Madeleine, in the mixture case, surely you can't be getting a global maximum of the likelihood because that's usually got by putting one component to basically concentrate on a single observation.
Yeah, sure.
And everything else fitted by the other component. So so you're getting a local maximum, presumably,
yes.
Both in the normal and the log-concave case. That suggests there might be more than one local maximum.
Yeah, so what we did was restart the algorithm from several different points and then pick the largest local maximum.
And hope for the best.
And hope for the best, yes. Yeah.
So again on the breast cancer example, if we were really going to fit a mixture of Gaussians, because both of those quantities were positive,
right.
we just take the log rate and then it would be an unconstrained thing and the local skewness would go away.
Yeah.
But your non-parametric approach is sort of not obviously broken on the positive quadrant. Do you think that it removes the need for that sort of pre-processing, or it's just that
Sorry.
So do you think it still might be worthwhile going through looking for transformations in
Functions that
input
would-
space, or do you think that as long as you're looking for sort of reasonably unimodal densities, you've got enough flexibility?
I think the unimodality is the kind of most important point, but I don't really know. I mean, yeah, I don't know. I haven't tried. Sorry.
I'm sorry, you might have said this, but the algorithm that produces the estimates, is it guaranteed to produce a piecewise linear spline?
Yes, because of the, I mean, because of the way you optimize over the kind of tentpole heights, so it'll it'll give you the sort of the heights corresponding to each observation, and then by taking the convex hull of those points, then you can recover that's going to be piecewise linear. So
The boundaries are between, essentially along lines joining the observation.
right, yes, yeah, by definition, that's just a property of these kind of functions.
Given that observation, have you thought of sort of cruder methods where you simply fix the spline points, if they equal space or something like that, and then try to fit a linear but suitably monotone spline?
Yeah, so that's something I've been thinking about. If you fix the pieces on which it's linear, then you can optimize more quickly. But it seems to be quite tricky if you really want to find the maximum, to think of a good way to move between the different possible triangulations. So it might be possible to do something like that, but I'm not sure yet. But certainly for a fixed triangulation, yes, it's possible to maximize. Thanks a lot.